Welcome all. Now we are going to discuss Theorem 8.4. The statement is a Banach space cannot have a denumerable basis. It is also called Hamel basis. Okay. So every Banach space cannot have a denumerable basis. This is the theorem. Now let's take a look at the proof. Let capital X be a Banach space. Assume if possible that X has a denumerable basis. Let it be x1, x2, etc. Okay. Denumerable means countably infinite. Okay, so this is a denumerable basis for the Banach space capital X. Now we are defining capital Ym is equal to span of x1, x2, etc. xm for m equal to 1, 2, 3, etc. So y1 is the span of the first element and y2 is the span of first two elements in the basis, and in general ym is the span of first m elements in the basis x1, x2, etc. Okay, so clearly each ym is finite dimensional, and so it is a finite dimensional subspace of capital X for every m. Okay, and so it is closed in X for every m because of theorem 5.4 b part. So we have each ym is a closed subspace of capital X. Now let the complement of ym be dm, that is ym complement equal to dm. Since ym is closed, each dm is open in capital X. Okay. Also by the definition, clearly we can see that the point xm plus 1 is not an element of the space ym. Okay, because ym is the span of first m elements. So clearly xm plus 1 is not an element of ym. This means that ym is not equal to capital X. And so by the theorem 5.6 c part, we can say that the interior of ym is equal to empty. This means that dm closure is equal to capital X, that is each dm is dense in capital X. Okay, the proof is in the brackets. If dm closure is not equal to capital X, then what happens? We can see that if dm closure is not equal to capital X, we can choose an element x element of capital X with x is not an element of dm closure, right? Okay, so by this we can see that there exists a neighborhood bx of this element small x such that bx intersection dm is equal to empty. That means that neighborhood does not intersect with dm. Okay, that is bx is fully contained in dm closure, which is dm complement, which is equal to ym. That means bx is subset of ym interior also, because we know that the neighborhood bx is open and ym closure is the largest open set contained in ym, and so bx is a subset of ym interior also. This means that ym interior is non-empty, which is a contradiction. Also already we have seen that ym interior is empty. Okay, so we have each dm is dense in X, and we have X is a Banach space, and by using Bayes theorem, X is a Banach space means X is complete, so intersection dm is dense in X using Bayes theorem. Okay, that means intersection dm cannot be empty. Let it be equation number 1. But we have x1, x2, etc. is a denumerable basis for the Banach space capital X. That means span of that x1, x2, etc. is equal to capital X. Okay, so if we take the union of all ym, we get capital X, right? So taking complements on both sides, we can see that intersection ym complement is equal to empty. That means intersection dm is equal to empty, which is a contradiction for equation number 1. So we have arrived at our conclusion that X cannot have a denumerable basis. So every Banach space cannot have a denumerable basis. This is the proof. Thank you.